And without further ado, let us enter into our sixth plenary session, which will be led by Mrs. Angelie, who is one of our own lecturers in the Industrial and Systems Engineering Department here in IPS. So let's not keep them waiting and give it to our moderator in charge. Mrs. Aga, the Zoom is completely yours.
Yeah, okay. Is my voice heard clearly today? Hello?
Clear.
Hello? Sorry. Is my voice heard clearly?
Yeah.
Yeah, okay. Thank you very much for Master of Ceremony for allowing me to continue to the next session. Good morning, everyone. I'm Ega Rizkia. You can call me Ega. I'm a lecturer of Industrial and Systems Engineering Department, the moderator of today's plenary session. Yeah, okay. Our speaker today is Dr. Josefa Angelie. Dr. Josefa is here with us all today. Good morning, Josefa Angelie. How are you?
You can call me Angelie.
Okay, Dr. Angelie. Yeah. Right. The time difference between Indonesia and the Philippines, I think, is probably about 1 hour. So it's morning there too, right?
Yes, that's correct. It's 9 a.m. here.
Okay, yeah. Thank you very much for coming to ITS, Dr. Josefa Angelie. I mean, because my background is also in the field of ergonomics, so this morning I was very excited to take this part on this session. Let me read the resume of Dr. Josefa Angelie. Dr. Josefa Angelie is one of the Assistant Professor 7 and Chair at Industrial Engineering Department, University of the Philippines, Los Baños, Philippines. And her research interests are human factors and ergonomics, especially in the effect of the arm on vibration. And she has received her PhD in Department of Design, Kyushu University, Fukuoka, Japan. And today's plenary session is about ergonomics in Industry 4.0. Okay, before the presentation begins, let me inform how the presentation will be going on. The first, Dr. Angelie will be present the material for 45 minutes and then 10 minutes for question and answer. After that, there will be a question and answer session. So if you have any question during the presentation, just type your question by clicking the link of Slido in the chat box. Okay, now allow me to welcome the speaker, Dr. Angelie, to deliver her material. Dr. Angelie, are you ready?
Yes, I'm ready. Can I start sharing my screen?
Yes, okay. Sure, for the share the screen.
I cannot share my screen as of now.
Yes, I think it should be the committee. Please help us to allow Dr. Angelie to share the screen. Mm,
I still cannot share.
maybe I can
I
help.
can share now. I can share now.
Okay.
Thank you. Thank you.
Yes. Okay, Dr. Angelie, the screen is yours.
Can you see my screen now?
Yes, we are can see your screen.
Okay. So
Yeah.
thank you for that warm introduction. Okay. So good morning to all the students, to the faculty members, and all the attendees of this event, the ITS Summer Camp 2. Okay, so for today, I will be giving to you an overview of ergonomic-related research on the physiological responses to hand arm transmitted vibration. So I will be sharing to you the different research and studies that our department were able to conduct through the years, which aimed to primarily improve and reduce the amount of transmitted vibration from agricultural machinery to the operators. So again, I am Josefa Angelie de Revilla. I am an assistant professor and current chair of the Department of Industrial Engineering, College of Engineering and Agro-Industrial Technology, University of the Philippines, Los Baños. So before I start, I would like to thank ITS for this opportunity to speak and to share our research here in the Philippines in UPLB, and for also inviting our students to this summer camp.
Yes, our pleasure, Dr. Angelie.
Okay, so let me start my presentation. First, let me give you a very brief introduction of how I started with this research. So my focus, my research interest or research experience is about the physiological responses to hand-arm transmitted vibrations. So initially, from our earlier research here in the Philippines, we started focusing on hand-arm transmitted vibration. But because of some limitations in the equipment, in the especially ergonomic equipments, we were not able to include or consider the amount of the effects, the physiological effects of such transmitted vibrations to operators. And so when I took my PhD in Japan, this was one of this specific topic was considered as the focus of my dissertation. Specifically, the main focus right now of the research is to develop sustainable handle grip that can minimize the negative impacts of vibrations. Okay. So for the next slide, let me briefly introduce to you the prevalence of occupational vibration. So we all know that in the early days, we are all using manual tools. However, due to industrial mechanization, these manual tools have been converted to mechanized or powered equipment. Primarily because we want to improve productivity and efficiency. So this is not just present in the agricultural sector. This can also be observed, and this is very prevalent even in the manufacturing industry. However, these power tools create vibration, can be transmitted through your whole body or to the hand-arm system. So my focus will be on the hand-arm system. The amount of transmitted vibration is not just influenced by the characteristics of the vibration source, it is equally influenced by the hand-arm biomechanics of the operator, meaning how strong you grip the handle, what posture you are imposing, something like that. And in the long term, continuous and long-term exposure to high level of vibration given the extreme grip exertion, awkward posture, these all can lead to what we call as hand-arm vibration syndrome. Okay. This can affect affect peripheral neuropathy or can lead to peripheral neuropathy, musculoskeletal disorder, and vasoconstriction. My main focus will be on the musculoskeletal disorder. And these can lead to permanent disabilities. So the critical stage when assessing the effect of vibration will be on the onset or during the short-term exposure. So in the succeeding presentation, you can see that our focus will be on the short-term exposure to hand-arm vibration, because we consider that this is the critical stage. This is the critical stage wherein we should be able to determine or discover the onset of HAV symptoms. Okay, so occupational vibration here in the Philippines. So agriculture is one of the main sources of livelihood here in the Philippines. In fact, 25 to 30% of the labor force is under this agricultural subsector. 17% of the 30 million hectare land area are arable land used for farming, and one of the top agricultural commodities is rice. When planting or when farming rice, usually the farmers need to first prepare the land. So as you can see in the picture here, so you first need to prepare the land before you can actually plant, or you can actually plant the rice or the seeds. So let me show you here on how land preparation is being conducted. So before that, let me inform that one of the main agricultural machinery being used to prepare the land for farming is the hand tractor. So this is an example of a hand tractor. So this is usually pushed forward at a slow pace. Sometimes it can be lifted or pushed downward depending on the quality of the soil. So let me show you a short video clip on how a hand tractor is being operated. So as you can see, it is being pushed, a hand tractor is being pushed forward to prepare the land for planting. And sometimes the operator lifts or push the hand tractor downwards. Now here are some of the research that we have conducted here in the department that relate to transmitted vibration in physiological responses. As I mentioned earlier, in the previous years, we were more focused on hand-arm transmitted vibration from a hand tractor and how it can be reduced. So here are some of our research related to that. We mainly focused on hand-arm transmitted vibration early on or previously because of some limitations in the equipment that we have. But eventually, we were able to also focus on the physiological responses to vibration in only in a laboratory setup. Okay. To give you a brief background here, so again, in our department, we have been involved in a series of studies that investigated the amount of transmitted vibration from a hand tractor to the operator. So in the early studies, only HTV or hand transmitted vibration were investigated, and these research were initiated by our previous department chair, Assistant Professor Layawin, and one of our faculty members, Engineer Yap. So together with some of our faculty members and students, we were able to create a series of studies that established a good foundation on the knowledge about hand tractor vibrations and how they can be minimized. So this was seen back then, given a few limitations in our resources, such as availability of ergonomic equipment, specifically the electromyography, we were not able to assess the physiological effects of hand-transmitted vibration to the operator. So this was seen as a significant opportunity and area for further research. Hence, I used this as part of my PhD dissertation. So with a wide range of available ergonomic equipment in my university in Japan, I was able to focus and I was able to consider the factors that can affect the physiological responses of operators from hand-arm transmitted hand transmitted vibration. Okay, so here are just the summary of our studies. Now let me give you a brief overview of each of these studies. So the very first study that we focused, that we considered, that we researched on, is the baseline measurement and analysis of hand-arm transmitted vibration from an ergonomically designed two-wheel tractor. So this was conducted in 2015. So to give you an overview of what we did here, so in here we used a test field with a total area of 6,000 square meters. So the field was composed of homogeneous soil in lowland condition. So the following factors are considered constant. So these are the forward speed, the engine speed, the environmental conditions, the worker-related factors. And due to land area availability, only 4 repetitions were considered. So there were 2 farming activity that we considered. These are the plowing and harrowing activity. So we considered 3 healthy operators with no physical ailments and are all familiar in using the hand tractor. So the hand tractor that we used is the UPLB AMD ergonomically designed two-wheel tractor. This is a diesel type tractor, and the initial design was based on the anthropometric characteristics of the farmers within the Calabarzon area or within our area. So when we measure the amount of vibration, we used the triaxial accelerometer. We located or replaced this on the engine, as you can see in this figure, on the hand of the operator, on the elbow, and on on the shoulder. The main task of the subjects or the operators were to operate the hand tractor considering the two implements for plowing and harrowing. So there were 4 trials for each implement or process. So each trial, the subjects were asked to, after each trial, the subjects were asked to rest for 15 minutes, primarily to dissipate the initial effect of the previous task. So during the hand tractor operation, the vibration amplitude from the 4 locations, the engine, the hand, the elbow, and the shoulder, were measured using the tri-eggshell accelerometers, and they were recorded using the data logger system attached to the accelerometer. So eventually, the recorded data was exported to MS Excel, and they were analyzed using Minitab and StatFit. So to give you the highlights of the results, so the amount from this study, we figured that the amount of transmitted vibration from the hand tractor engine to the hand, elbow, and shoulder exceeded the allowable threshold value, or they all exceeded the exposure action value and exposure limit value, which are the two, we can say that the safe values required by the international standard. So with the vibration values presented, it is possible that 10% of the operators can acquire vibration white finger, or this is quite similar to the hand-arm vibration syndrome, after 1.5 or 1.58 and 1.67 years of plowing and harrowing, given that they work for 8 hours a day. So given this result, the results that we found here are actually very significant, and the results led to various researches and studies which aim to minimize or reduce such vibrations discovered here. Now, the second study focused on that, reducing the amount of transmitted vibrations. So this study is the optimal handle grip and engine mount combination for minimized hand vibration from gasoline hand tractors. So this is the abstract, and this is how we conducted the experiment. So basically in here, it was conducted, unlike the first study, which was conducted in an actual field operation, this study was conducted in a laboratory setup, outdoor laboratory setup. So one male subject was chosen in the study. His skills and familiarity in handling the tractor were not of primary consideration, since the experimental task only required him to hold the hand tractor in idling operation. So various handle grips and engine mounts available in the Philippine market were identified through market research and survey. So from this research and survey, the results were further categorized only among those which can fit the handlebar of the existing hand tractor that will be used in the study. So a few handle grips were then determined. These included the BMX, the mountain bike, the motorbike, and the tennis rubber tape. All were found to fit the handle diameter of the hand tractor. Meanwhile, three engine mount brands were considered, namely Isuzu, Suzuki, and Mitsubishi. So the tractor used in this study was a gasoline-powered tractor. So there are 3 replications for each trial, or for each trial. Each replication lasts for about 5 minutes. They were done in So the first task is to collect the vibration on the hand of the subject during control condition, meaning no handle grip and no engine mount were installed during the control condition. So then the vibration during the different combinations of handle grips and engine mounts were recorded. The percentage reduction between the control condition and the various experimental conditions were computed to determine which optimal combination can be proposed. The vibration on the hand was measured using a tri-eggshell accelerometer similar to that used in study 1. So again, the vibration was recorded in the data logger system. Aside from the optimal combination of handle grip and engine mount, the study also measured the economic factor, which is the reduced vibration per unit cost. So to give you the highlights of this study, So during idling operation, it was found that having a handle grip and engine mount significantly reduced the amount of vibration transmitted to the operator. Okay. Although the addition of the handle grip and engine mount entails an increase in the cost, the amount of transmitted vibration may be reduced by approximately 44%. So the next study focused on comparing the difference or the effects of having a diesel-powered tractor and a gasoline-powered tractor. So remember in the first study, the hand tractor that was used is a diesel-powered. On the other hand, the second study considered a gasoline-powered hand tractor. And so the third study focused on how commercially available vibration dampeners, specifically handle grips and engine mounts, can reduce the amount of vibrations on both diesel-powered and gasoline-powered hand tractor. Okay, so similar with study 2, it was conducted in the laboratory grounds of the university and one male subject was chosen. So the same type of commercially available handle grips and engine mounts were used. So the tractor used in the study was the same two-wheel tractor in study 2, but this time there were two engines. Two engines were used, one diesel-powered and the other one is and the other engine is a gasoline-powered engine. So the engine 1 is a diesel type engine, the Kama KM170F, and the engine 2 is a gasoline type engine, the Kenbo KB 5.5 engine. The two engines were interchangeably placed on the tractor for testing. Okay, so 3 accelerometers were again placed on the hand, elbow, and shoulder of the operator to determine the amount of transmitted vibration. To give you a brief highlight of what we have discovered here, so this study presented the comparison between the transmitted vibrations from gasoline and diesel-powered hand tractor engines. During idling operation, the vibration from gasoline and diesel-powered engine did not differ significantly. Transmitted vibrations from both engines were reduced by using BMX and mountain bike handle grips with the same model of engine mount. And the reductions are approximately 35% for diesel-powered engine and 52% for gasoline-powered engine. Okay, so the next study again focused on using handle grips, but this time we tried to investigate substitute handle grips and vibration, substitute handle grips and engine mounts. Because of the cost to acquire or to purchase the commercially available handle grips and engine mounts as presented in studies 2 and 3, we considered the capability of the farmers and the operators to actually purchase this additional materials. So if they do not have enough money, at least they have substitute materials which they can use to minimize or reduce the amount of transmitted vibration. And so that became the focus of the study, to determine or to introduce different substitute vibration dampers or dampeners, such as handle grips and engine mounts, which can also reduce the amount of transmitted vibration. So this study followed the methodology of study 3. So the main distinction is that this one used substitute materials instead of commercially available materials because of the cost it would entail to acquire the ones in the market. And as I mentioned earlier, we considered the capability or the capacity of the farmers to buy commercially available materials. And if they do not have the capacity to do so, then they can just use substitute materials. So for the substitute materials, for the handle grips, we used bicycle tire inner tubes, bicycle tire outer tubes, air conditioning insulators, and synthetic leather and cotton cloth. For the engine mounts, we used rubber pads, jeepney tire sidewalls, and car tire sidewalls. Again, 3 accelerometers were used. Each was placed on the hand, elbow, and shoulder of the operator. To summarize the results, with the entailed cost of acquiring commercially available handle grip and engine mount, it is suggested to explore the application of substitute materials. So during idling operation, installing a handle grip made of air conditioning insulator combined with a car tire sidewall as engine mount resulted to approximately 55 to 60% reduction. So this is quite, I cannot say significantly higher, than the commercially available ones, but it's obviously higher than, the reduction is higher than the commercially available ones. This created a cheaper alternative for commercially available materials, which is more feasible for the farmers to use. Okay. Given studies 1 to 2 to 3, I think we already explored the feasibility of having handle grips and engine mounts. And so the next study focused on a more proactive approach wherein we tried to redesign and fabricate a different handlebar structure for a hand tractor, which can suppress or minimize the amount of transmitted vibration. Okay. So this study investigated 4 handlebar structures, the original one. So this is the original one, and 2 designs were benchmarked on the initial design of Burirat and Kanyakam in 2007. And the 4th design is an improved design or improved handlebar design, which came from the good characteristics of the first 2 designs from Burirat and Kanyakam. So there are essentially 4 handlebars that were tested here. The original one, the 2 designs taken from or benchmarked from the study of Burirat and Kanyakam, and an improved handlebar structure, taking all the positive characteristics of the 2 initial designs. So it is important to note a few limitations of this study. So one is the materials used in fabricating the new handlebars. So the study only used black iron steel because of its availability, affordability, and compliance to the standards set by the Philippine Agricultural Engineering Standards. Second is the evaluation of the effectiveness of the handlebar structures, which only considered the daily vibration exposure, structural mass, and vibration reduction. All other factors were not considered in the evaluation of the handlebars. So similar with studies 2 to 4, it was conducted at the laboratory grounds of the university, and 1 male subject was chosen. The same hand tractor was used, which was powered by a 5.5 horsepower gasoline engine. The vibration magnitude was again measured using a triaxial accelerometer, and it was recorded in the data logger. The accelerometers were placed on 3 locations: the handlebar tractor connection, and the base of the engine. Similar with the previous studies, the testing was done under 3 different engine speeds with 4 replications for each speed. So each replication lasts for 1 minute, wherein 60,000 data points were gathered. So the data were analyzed and compared using the analysis of variance, and Tukey's method was used for multiple comparison. So to give you the highlights of the results, the design was benchmarked on the study of Burirat and Kanyakam, the principles stipulated in PAES, and the engineering design process. With the new handlebar design, the amount of transmitted vibration from the engine to the operator was significantly reduced. The new design is also more economical and has a lighter weight than the original handlebar design. Now, the succeeding studies will be focusing on the physiological responses of the operators from hand-arm transmitted vibration. So the first study is about exploratory study on the impact of handle vibration on the hand and forearm. So as mentioned in the previous slide, slides or in my previous discussion, the general limitation of the earlier studies, the first 5 studies, was that they were not able to assess the physiological responses of the subjects. Okay, only the level of vibration and how it can be reduced. So hence the following research focused on the consideration of this important matter, which is the physiological responses of the operators. So in this first study, 7 young male adults were recruited without any long-term exposure to vibration and have not had any recent injuries in the hand-arm area. The vibration source, as you can see here, is a custom-made vibration table installed with a fabricated handlebar structure that simulated the level of vibration exhibited by the actual tractor and the hand-arm posture of the operators when using the machine or the hand tractor. The experiment was done in an indoor laboratory setup, and the main task of the subjects was to hold the handlebar for 5 minutes under 2 conditions. First is without the presence of handle vibration, and the second is with the presence of handle vibration. The activities or workload of 4 selected forearm muscles were measured using a surface electromyography during the 5-minute task performance. Pre-task and post-task tests, including maximum grip strength test, and the 9-hole pegboard test to measure finger dexterity, maximum pinch strength test, 2-point discrimination test to measure finger sensitivity, and subjective discomfort rating along the upper limb were performed. Paired t-test and Wilcoxon sign rank test were used to test the significance of the values. So to summarize the result, or to highlight the result, so in this study, we were not able to monitor the level of grip exertion during task performance. And so with unmonitored grip exertion during a 5-minute handle vibration exposure, the effects on forearm muscle activities and various hand functionality tests were not observed. And so this led to the next study wherein we tried to monitor, or we monitored the level of grip exertion during task performance, or when the operator is handling the vibrating handlebar. So the next study is the early effects of short-term exposure to mid-range vibration frequency on the hand and forearm. Okay, so in this study, 14 young healthy male adults were recruited with the same inclusion criteria as the previous study, or as with the same inclusion criteria as study 6. The same vibration source was used, only with minor modification or improvement on the handlebar attachment frame. A same indoor laboratory condition was applied, and the pre-task and post-task tests include grip strength test, pinch strength test, finger sensitivity test, finger dexterity test, and subjective discomfort rating. The main task is to hold the handlebar for 5 continuous minutes while forearm muscle activities and heart rate are being measured. So this time, the level of grip exertion during task performance was constantly monitored. So as you can see in this figure. So we provided a computer monitor in front of the participant to assist him in monitoring the level of grip exertion that he is actually exerting during the 5-minute task performance. So it was instructed to maintain his exertion at 30% of his maximum grip, as you can see in this figure. His grip exertion should be within this level. So we have here a boundary, an upper bound and a lower bound, wherein his grip exertion should be maintained within these bounds. Okay, so similar with study 6, there are 2 task conditions. First is without the presence of handle vibration, and second is with handle vibration. So to summarize the results, so now with constantly monitored grip exertion during the 5-minute handle vibration exposure, the effects on forearm muscle activities and various hand functionality tests were evident. So the effects of sustained grip exertion for 5 minutes alone led to decreasing forearm muscle activities, meaning tired muscles, reduced grip and pinch strength, elevated heart rate, and higher perceived discomfort along the upper limb. Now combining this with handle vibration, finger sensitivity and the ability to grip the handle consistently were also reduced. So the next study dwelled deeper on the specifics of the biomechanical factors that can affect the amount of transmitted vibration. These include the level of grip exertion and your forearm posture. So this study is about the effects of 2 grip force levels and forearm postures on hand-arm transmitted vibration and physiological responses. So in here, 16 young male Healthy adults were recruited. Same inclusion criteria were used. Same vibration source and handlebar attachment frame was used. In here, 2 handlebar structures were tested. The first one is a straight handlebar, as you can see in this figure. Straight handlebar, which encouraged a pronated forearm posture. And the second is the same bullhorn type, this one, handlebar structure that encouraged a neutral forearm posture. So the level of grip exertion was also categorized as mild, which is 10% of the participants' maximum grip, moderate, 30% of the participants' maximum grip, and hard, 50% of the participants' maximum grip. The main task is to hold the prescribed handlebar, either the straight one or the bullhorn type, using the prescribed handle grip exertion for 5 minutes while vibrations at baseline on the handle, wrist, and elbow are being measured, as well as the forearm muscle activities and heart rate. Pre-task and post-task tests, including grip strength tests and subjective discomfort ratings, were again measured. So similar with study 7, grip exertion was monitored in the same manner. So 2-way and 3-way repeated measures ANOVA were used, and Bonferroni correction was used for multiple comparisons. So to highlight the results, we can see here the mean percentage of grip strength reduction. Evidently, it can be observed that hard grip led to higher grip strength reduction. No significant difference between the two forearm posture. Also, the subjective discomfort rating provided significant results or significant difference in terms of having a hard grip, in terms of using hard grip than a mild grip. Okay, the mean percentage maximum voluntary contraction or muscle activity, also the mean percentage muscle activity between hard grip and mild grip also differs significantly, as you can see. So this is the forearm muscle activity during hard grip, and this one is for mild grip. So you can see the main difference of the two. However, forearm posture did not influence the amount of muscle activity or the level of muscle activity. Okay, so to highlight the result, when a certain task involves strongly gripping a handle, the forearm posture on the handlebar structure must promote a natural or neutral forearm posture to minimize the physical workload brought by the presence of vibration. When a certain task involves mildly gripping a handle, meaning about 10% of your maximum grip, then either a pronated or neutral forearm posture is okay or is recommended.
Sorry to interrupt you, Dr. Angelie. A kindly reminder that the deliver time is 10 minutes left.
Okay, thank
Before
you.
we continue to question and answer session.
Thank you. Okay, so the last study that I will be sharing to you will be the effects of various handle shapes and surface profiles on the hand-arm responses and comfort during short-term exposure to vibration. Okay, let me just give you why this study was established. So after giving a good foundation, somehow good foundation on the physiological impact of vibration to the upper limb, this study aimed to investigate how these negative impacts can be mitigated, specifically through the application of customized handle grips. Because from previous studies, it was proven that having a handle grip and engine mount can reduce the amount of transmitted vibration. And knowing that, can this also reduce the amount of physiological impact to the operator? Okay. So very briefly, let me just show you the handle grips that I used. Yeah. So I used 6 handle grip designs, 3 different shapes, circular, double frustum, and elliptic. And I also considered 2 surface profiles, a smooth and patterned surface. The main task is to hold the vibrating handle for 3 minutes, while vibrations at baseline, handle, wrist, elbow, and forearm muscle activities are measured. Pre-task and post-task tests were also performed. This include grip strength test, finger sensitivity test, and subjective discomfort and grip comfort rating. Paired t-test, Wilcoxon sign rank test, two-way repeated measures, ANOVA, Friedman test, were the statistical tests used in the study. Okay, here are the results. Just to summarize, handle shape influenced transmitted vibrations and grip strength reduction, while the surface profile influenced finger sensitivity and perceived comfort and perceived discomfort and grip comfort. Now, the main limitation of this study is that of the four studies 6 to 9, the main limitation is that they were all done in a laboratory setup. And so, our present research will now focus on developing a sustainable handle grip, which can minimize the hand-arm transmitted vibration from agriculture machinery in actual farming operation. So these are just the factors that were established to which can affect the amount or level of vibration transmitted to the operator, as well as their physiological responses to the operators. So the main objective of the present research is to develop a sustainable handle grip that can minimize the amount of hand-arm transmitted vibration from agriculture machinery used in the Philippines during actual field operation. Okay, that's the main objective. And so let me just show you our experiment flow. First is to create a baseline assessment of how the vibrations are being transmitted during actual farming operation, how much physiological responses, or what are the physiological responses of the operators to such level of vibration during actual farming operation. The next step is to design and fabricate sustainable handle grips. The next is to evaluate the proposed designs, and finally to create recommendations. So this is just what we did when we are establishing the baseline measures, specifically the baseline measures of transmitted vibrations, muscle loading, existing hand functions, and baseline assessment of discomfort and comfort of actual farmers, of operators of farm machineries. Let me just run down the tools that we used. So we used the same accelerometer and data logger to measure and record the vibration acceleration on the engine and handlebar. We used surface electromyography to measure and record the muscle workload or activity of the forearm muscles or the arm muscles. So we attached the EMG, surface EMG on the forearm, the biceps, and the elbow and the shoulder. We also use hand dynamometer to measure and record maximum grip and pinch strength. We assess subjective ratings using subjective rating scales for discomfort and grip comfort. This is to quantify the upper limb discomfort and the level of grip comfort when using the existing handlebar. We also measured blood pressure to quantify cardiovascular health of the farmers. Since this time, in this experiment or in this research, we are considering farm operators. Unlike the previous studies wherein I considered young healthy male adults. We use the 9-hole pegboard test to quantify finger dexterity, 2-point discrimination to quantify finger sensitivity. Okay, so the main goal here is again to develop a sustainable handle grip. We are still in the early stages of the research, so we are now finalizing the baseline assessment. We have yet to design the handle grip. We have yet to fabricate the handle grip, but this part of the research will be our next focus after we assess the initial results. Okay, so these are just some of my references, the references that I used in this study. What else? So, okay, so that's it for my presentation. So thank you it is my pleasure to share our ergonomic progress here in the department, specifically now that we are in the Industry 4.0 era where manual tasks are being converted or being replaced by powered ones. So nevertheless, it is equally important to investigate how these newly developed equipment can aid productivity and efficiency during operation. So thank you all for listening.
Okay, thank you very much, Dr. Angelie, for giving us such informative and interesting material. Okay, now we come to the question and answer session through Slido, and I like to have maybe the question from the participants, and I will choose the most interesting question. Okay, committee, thank you for helping me to show the Slido. And we have already many questions here. I will read a question from the participant, and Dr. Angelie will answer it. The first one is coming from Vince, asks about could Industry 4.0 technology, such as augmented reality and Internet of Things, aid in work ergonomics for even its research?
I think
Dr. Angelie,
I think these things, augmented reality and Internet of Things, can definitely aid in work ergonomics or in this research. However, at this stage of, or given our progress in this research, I think it is still necessary to first establish the baseline values. Once we have those, then we can proceed with using such technologies. But definitely, these technologies, augmented reality, Internet of Things, can definitely help in the progress of this research, and even in other ergonomic research.
Okay, thank you, Dr. Angelie, for a very detailed explanation. And for the second one, questions from Anonym asks about, based on your experience, Dr. Angelie, what will be the future trend on the ergonomics handle, maybe in terms of shapes or any other advanced technological characters?
Based on my experience about this, the main goal to really eliminate the physiological effects of vibration to humans is to remove the equipment, or to eliminate vibration from the equipment. However, for now, we cannot do that, since because of the engines that we use, because of the mechanized equipment that the electrical equipment, mechanized equipment that we use, we have yet to discover on how to remove vibration from those coming from those tools. But the idea would be to actually remove vibration from those equipment, from those tools. If you can do that, then that's the ideal setup.
Okay, thank you, Dr. Angelie. And for the last one, question from Moses asks about, as opposed to dedicated handle grips for each machine, could gloves be developed which would help in the reduction of vibration experienced by the user?
We actually already have gloves to minimize or to control vibration. What do you call it? But we already have this. However, my main concern here is that when you are in the field, the temperature is really hot, so it is quite difficult to use thick gloves. The one that we have now in the market, but perhaps we can develop a different kind of gloves wherein it will be more comfortable for the users to use, especially when under a very how do you say, extreme environment.
Okay.
For example, very cold or very hot environment.
Yeah. Okay, Dr. Angelie, due to we have some spare time, so we can continue to the next question, around 2 questions more. And the next question is from Anonym, asks about, sorry, can committee to slide the question? Yeah, okay. With the emerge of Industry 4.0 era, how will ergonomics can help in boosting worker performance with the interconnected things?
Yeah, can you clarify the interconnected one?
Yes, but who is the asked this question? Interconnected things maybe in the work in the operator itself or integration. Yeah, with the integration things.
The question is quite unclear to me, but can you clarify the question?
Maybe we can change the questions for the next one.
But once the student clarifies this question, please message me so I can answer.
Because we don't know who is the
Ah.
sent this message.
Okay. Okay.
Yes. Okay, anyone from the participants who send this question, maybe can raise your hand to ask directly to Dr. Angelie. Or maybe we can change to the next questions if you
Yeah, we
are.
can do that. We can
Yeah.
do that. The participant can just message me or can message Engineer Alan. So Engineer Alan can redirect the message to me.
Okay. Yeah. Okay, for the next question, could you please elaborate on Industry 4.0 technologies that are used in the studies you have mentioned, Dr. Angelie? Thanks.
Actually, for this one, my intention when I made this presentation is to give everyone an idea on how ergonomics evolve and how ergonomics can eventually adapt to this industry 4.0 era. Because previously, if you can previously well, just to share, previously when you are doing farm operation, you are using carabaos, animals, to pull the implement and prepare the land. Right now, we were able to develop, or every agricultural country were able to develop hand tractors. However, this equipment creates some negative impacts to the operators. And so my intention when I made this presentation is to give everyone an overview on how ergonomics evolve and how it can be applied in agriculture and hopefully or eventually in the industry 4.0 era.
Okay. Thank you, Dr. Angelie, for the explanation. And we can move to the next question. Is stop for the Sophia. Okay, question from Sophia asks about what is the current position of the Philippines in terms of developing technological advancement for ergonomics?
I cannot answer this for the entire country, but for the department, it was, as I mentioned earlier, it's quite slow. But that's why we are doing research so that we can present, we can let everyone see that ergonomics is an important matter to consider in designing a workplace, in designing an equipment, a tool. So I cannot answer for the entire country, but for the department, I can say it's quite slow. That's why we are continuously doing research to.
Okay, thank you, Dr. Angelie. And for the last one, I think, does the design in your study also pay attention to ergonomic dimensions? Because as far as I know, the size of the tool will affect work comfort. This one question from Camila.
Yes, the design paid attention to ergonomic dimensions. In fact, the proposed handle grip designs that I considered were all within the prescribed diameter, which is around 30 millimeters.
Okay. Yeah. It's very interesting. We learn of a lot of from Dr. Angelis about ergonomics in the industry 4.0. And finally, because time is limited, we will end this fifth session. Before closing this session, I will give a little brief summary of the material related to the ergonomics in industry 4.0 from Dr. Angelie. So the Industry 4.0 program is bringing business or something like a company or business to rethink their processes by considering human factors, ergonomics, and sustainability issues. Even in agriculture and Industry 4.0 has also been used. This is due to the fact that ergonomics can be used in a variety of industries, such as optimization of the safe use in machine for user and can even reduce operating costs. And if there is an opportunity, because my background is in ergonomics also, like Dr. Angelie, maybe next time or in the next occasion, I would like to collaborate to do research because research related to hand-arm vibration is very interesting, especially since Indonesia is known as an agricultural country with most of the population working in agriculture. Maybe we can compare the data of Indonesia's operator and Philippines operator or something like that. Okay, I would like to thank the speaker for the informative and interesting presentation and all the participants who for their very active participation. Thank you, Dr. Angelie, for being willing to be a speakers at this year's summer camp. Hopefully we can meet again on another occasion.
Thank you, thank you. The research invitation is really a good idea. Thank you.
Yes. Okay, we can keep contact to the next discussion maybe. Okay, finally, give a virtual applause for the speaker and for you all. I'd like to apologize if there are many mistakes made by me as a moderator during this session. I handed the screen to the Master of Ceremony to continue the summer camp agenda. Thank you very much. Good morning, Dr. Angelie and everyone.